Well, in this has been part of the work that I have been doing in collaboration since many years. Probably we have been working in this code about 12 to 15 years. And the main goal is to develop a multi-phase flow simulation. Okay, I cannot go to the next.
Can you try again? If you pointed to the, you come on this side.
I'm doing it right. You can press the next one, it's fine. Go to the next one. So as I said, like the main motivation is to have this multi-phase flow code. And when I'm meaning like a multi-phase flow, we are developing an Eulerian approach where the sediment and the fluid are composed by proportions, fractions of each one. So meanwhile, in this process, we wanted this three-dimensional code. We have been studying several test cases for to validate this problem. One of the last test cases like we reach is like we have a cylinder and how is we want to study the erosion of this structure in the action of waves. So that's where like we start trying to push the code each time more and more like, okay, it goes. So for example, for this test case, I like to always start with this slide because here we can clearly see one of the main problematics of these test cases, that is not the meshing, but it's the number of elements that are required close to the structures. So if we want to make a multiply test case, like every time we are requiring more and more number of elements. But even more like the test cases like we wanted are directly related to the three-dimensional flow. So that means like the number of layers that we have in the vertical direction also increase. So for this test case, like we can play the video number one. So I wanted you see one of the simulations that we were having. We were happy with this one. We were generating nonlinear waves, highly nonlinear waves that actually we have some data to compare from some colleagues from Italy. And if you can see, here is the structure, in this case, the circular cylinder. This is how the waves are behaving close to the cylinder. And we see actually what we wanted, how when the wave hits the structure, we see how the behavior is not just only in the back of the cylinder, but also in the front of it. And it's this jet that is forming in the front of the structure, like generates this horseshoe vortex and start eroding like the sediment that we found. Okay, so here are the problems when they start. We have the code. We know like the code works well. You can keep going. But to having only the hydrodynamics for this one, to having only a few seconds of this simulation, we are spending weeks of computing. And in this one, like, for example, like the video that I'm showing you, probably we get it like in 2 weeks using at least 64 processors in an MPI code. So that's too much. And talking about a sediment, the time scale is completely different. We are talking about hours of real-time simulations instead of seconds. So how is this code? This code is based in the Navier-Stokes equations in sigma coordinates. In this way, we avoid to remeshing due to the free surface that we have it, but the equations become more complicated. So in the last years, we have dedicated so much effort to try to do like a very efficient code, not only in terms of accuracy, but also in terms of performance to get as fast simulations as we wanted. So at the end, all these how hard your or how difficult your numerical method can be applied, at the end, everything reduces to solve linear systems. In our case, like we have a linear system related the cell center of our elements with the nodes of this one. And of course, as everyone knows, like in this type of conference, like more elements we have, more nodes and more cell centers what we have. So in this case, like the solver like we are using, we have seen like the SOR method have worked pretty well for us in these ones. Like this is a very classical method, sequential, but when you're doing like in the multicoloring, when your code is stable, like actually the Poisson equation that usually is the bottleneck of the simulations results in almost the same number of iterations as the fluid. Like everything is proportional at the end, only like 3, 4, even 5 iterations, you can reach a very high performance with these ones. Okay, so what we have it so far. Okay, we have going in 2 different directions at the same time. First, we are, the first one is trying to use the CPU. Everything, all the code is parallel in NPI using block domain decomposition. Lucky for us, we have access to different supercomputers. We have in Canada, we have in France, we have in China, we have in Mexico. So our problems is not in terms of accessibility to the number of nodes that we want. Our problem that is happening right now, it's in terms of scalability of our problem. So, but at the same time, we have been working with GPUs, okay? So, but so far, we only have parallelized the Poisson solver related to the pressure of this equation. And here is just one slide that you can see about how we have been working with CUDA and with the GPUs trying to parallelize this code. I'm very happy with the results that we are having with this one because we, sorry, because we only want only one GPU, we have been getting like around 100 times faster the code. So this is, for us, is pretty impressive because in your office, you can have your computer, you run it, and you are having like almost the same efficiency like we have been using like the supercomputers that we have it. The bad part is like we haven't parallelized everything in our code. And on the other hand, or parallelization using an MPI. And here are the kind of problems that we are dealing when using a block domain decomposition. Due to the structure that we have it in terms of the test cases that we are using, like the domains are becoming every time more complex. In terms like, here is like related with the scalability what I'm talking about. Like even when we have access to 100 of cores to run this one, there is one moment like the code do not go like faster than 100 times. So here, like just to talk a lot about the test cases that we are doing, we are not doing anymore one cylinder. We are going forward to this one. So in my case, I wanted to try this configuration. This is a very basic configuration. This is the triangular one. And why with this configuration? Because we have data to compare about that. We have other recent simulations that have been done it in this test case, but with low Reynolds numbers. Like, as you know, depends of the low Reynolds number that you use is the kind of behavior that you have it. So this is the kind of configuration that we are using, the 3 cylinders in this equilateral configuration. As you can see, we are adding some extra element there, like this, like the distance between this one. This is an extra component like we are including, but we can manage the different test cases for this one. This is the complete computational domain that we are talking about. As a first step, we are just fixing the top to be rigid, and the bottom can be varied, and depends of the boundary conditions that you put in the vertical direction is how the test case they will be, like if you use free sleep or a fix or a mobile bed. And we start with the simplest ones, like with low Reynolds number, like in this case, and everything was as expected. You can see here, like the difference of the simulation between one cylinder and the three cylinder. Again, with this low Reynolds number here, we are having like actually a two-dimensional behavior as it was expected, but we begin to see the differences between one and the three test cases. Like, for example, the recirculation vortex that is behind the cylinder. Now, like, we can see like this complex interaction behavior that is happening here. But the most interesting cases is happening when you have higher Reynolds number, like when you have like a fixed bed. So in this case, going from 100, now we are going to 46,000. This is a huge gap between these two cases. But actually, in this Reynolds number is where the erosion happens. The live bed conditions to get the score around the cylinder is in this range of Reynolds number. Oh, so we have tested this before successfully with only one cylinder. So we want to know right now how it behaves with this new scenario. And here are a few of the simulations that we had. Here we are comparing again, like the one cylinder or the three cylinder one. And the first thing that surprised me, at least in my case, here is like the typical behavior. You see the three vortex structures that you have it in front of the cylinders. And here, you don't appreciate that very much, but there is one main vortex that is happening just in front of the set of the structures. Like the main vortex is not happening just in front of the first cylinder. It's really, really, really hard to see. Here, I will show you in one moment a two-dimensional view, but this is like what will happen in one cylinder. But in the 3-1, you can see in different colors what is happening just in front of each structure. But the main behavior of the horseshoe vortex is happening as the three structure when one unit in itself. And you can play the second video here. Here is just one video about the simulations that we are doing. And meanwhile, this is performing, coming back again to the performance of this code. Like, again, like this is easy in terms of high performance computing because we only have to simulate a few seconds. With a 100 unit of times, you can get this kind of simulations, approximately like for this one day. Okay, so you can work pretty well. Like with 64 processors, with the supercomputer, we can get like these simulations in 1 day. So in terms of this academic developing of this research, this is a decent time to work. But what happened? Okay, this is like this slide. Like we want to show. Like at the end, I am a mathematician, and I love symmetry. And there was a lot of symmetry happening here. Like as I was telling you, these are the three structures that we have it here. Besides the vortex, the small vortexes that happen in the cylinders, there is one thing, main vortexes that is happening outside of this structure working as an entity. Okay, my hypothesis right now, like that's the thing that I have been working to, it's like independent of the rotation of this one, I will still have in the same vortex. Okay, I don't know, like this is like very recent results, but also the location of this main vortex is happening depending of the position of the three cylinders. For example, like the last circle is centered in the last cylinder, for instance. So going back to the last part of the simulation, here comes like the sediment. Now we want to what's the case we are interested to is the erosion around the cylinders. Meanwhile, like for the other ones, in only few seconds, we need to run hours of real-time simulation for this one. In order to these test cases stabilize, we are talking about 2 hours of real-time simulations in terms of non-dimensional computational units. Meanwhile, the hydrodynamics happens with 100. In this one happens in 30,000 units of time. So we are talking about like a huge difference of this one. And meanwhile, the low Reynolds number only needs like a few number of layers. With 20 layers, you have it. In this one, you have more than 100 to at least to get like the horseshoe vortex that is happening around this structure. We can play the last video that I have it here. And this is what is happening. So this is the point like we have reached. Like now we have 2-3 weeks to studying these test cases, like using all this computational power. This is too much for us. Like you can work like that because that's the only option that we have it right now, but it's too slow. Okay, so this is like one of the pushing ways to do research right now. It's like how we can improve this code, how we can accelerate these ones to get sediment results, not now in weeks, but in days. Okay, so that's the way that I'm going in this one. It's just the last slide, the last one. Okay, it's a little bit while I was talking. Meanwhile, low Reynolds number, even with few number of processors like a 16 working in a workstation, you can get something in 10 minutes. It's really easy. But now we are talking like here, like only to have these 100 seconds. That will be around 5,000 units of times in this case, working with 5 million elements. That is not that high. We are using like taking weeks of simulation. So this is, for us, is slow, very slow. So we want to work in this way. The first solution for the last slide. Yeah, okay. The first way to improve this one is completely going with GPU. Okay, this is the first step because we already have the experience working with the Poisson. We can extend it. This one with the full code. That is the steps that we are going forward to doing that. Hopefully, like at the end of this year, we will have this one, and we're expecting the 100 times performance. That will be only with only one GPU, at least amazing for us because we are not depending of the number of users or of the supercomputer that we are having access. But my main challenge for me is how to deal with the scalability of the MPI version of the code. Like right now, basically, we have vectorizing everything that we have it. Like this is the first improvement that we have done it. But you know, with these academic codes, when you first develop, you develop as you can. You know, the first goal is that it works, that reproduce correctly the physics. Okay, and now we are going to the more to the computational part, like working with my computer science colleagues, working in the management of memory, vectorizing everything. Now with optimizing everything that we have it to try to get the best simulations as possible. Like, and that's it. That will be everything. Like, okay. Well.